Hi, today we will try to implement a buffer overflow attack. So for this, what we require is a program that has certain vulnerabilities. So I have already written one such program and I will be showing you that right now. Okay, so as you can see, what I have done here is I have allocated a buffer of character type of size 400 and I have used the strcpy function to take in input from the input buffer from the terminal and save it into the buffer. So the problem is that the strcpy function does not limit the number of characters that it takes in. So we can use this to our advantage to create a buffer overflow attack. Now what we are trying to do is we are going to create a no-op sled. So what we will do is we will change the buffer in such a way that there are a lot of no-ops here. There is the shell code after that, and then we adjust the size of the buffer using some trash value, and we place in the right return value such that that will be the place that the program returns to after execution. So it comes to the no-op somewhere here in the no-op and it falls down to our shell code and the shell code gets executed. So this is our plan of action. Now there are a lot of protections that are in place for such attacks to not happen. So we need to disable that one by one. And first we will be disabling the ASLR flag. This is the address space layout randomization flag. So we can use a simple command to do that. So this is the command. We are changing the value of this randomize underscore va underscore space flag. Okay, so as you can see, the value has become 0. Now after this, what we will do is we will compile the program exploit.c using certain flags. So these are the flags. What we are doing here is we are making the stack executable and we are disabling the canary protection. So these are two things which stop people from performing the buffer overflow attack. So using these flags, we can disable all these protections and compile the code. So now we have a binary ready, which we can use in the GDB. So we provide this as an input to the GDB. Okay, now we know that the the size of the buffer is 400. So first what we will do is we will run the program with an input of size exactly 400 and see what happens. Let's put in any value, maybe bees. Okay, so the program exited normally, but this is not what we want to see. So let's just put in a breakpoint and then run the same command. Yeah, now we can see all the registers, all the values where they are stored and all the instructions that are being done. So here we can move instruction by instruction using the ni command. We can see that add is the next instruction that has been staged to occur. So similarly, we can see where the base pointer is and where the stack pointer is. So we see there's a difference because the value has the size for our buffer has been allocated, and also other parts of the execution stack. Okay, so we do not expect anything to go wrong here. So the program has exited normally. Now what we do is we try to break the program by increasing the size of the input that we give. So instead of 400, let's try 405. Okay, now we will go instruction by instruction. So the next instruction is the call instruction, which is the function call to strcpy. So after this instruction, what will happen is our buffer will be flooded with a lot of Bs. Okay, so here something interesting has happened. The value which RBP points to has changed to 5 Bs. So the number 5 is exactly the same as the number that we increased the input size to, size by. So one thing we have figured out is that we can change the value of RBP by increasing the input size. So we keep going, and the program has terminated normally. Now we again increase the size, maybe 408, and we move instruction by instruction until the call command. Okay, so here after the call command, what has happened is the 8 Bs that we inputted extra has come to RBP. So now the next command to be executed is leave. What happens when leave is executed is the value that is being pointed to by RBP becomes its value. So as the legend shows, white stuff are the values. The RBP value has become 8 Bs. So from this we understand that we can completely change the value of RBP, and we will see whether it has any effect. So as we move forward running the program, we see that we encounter a error. So the problem here is that the register RBP may have held some value that was useful or being used by some other program before calling this, the exploit.c program. So what we have essentially done is we have replaced whatever was the value at RBP by 8 Bs, and this has caused problems after exiting from the main of our program. But this is not what we are trying to achieve. What we are trying to achieve is change the return statement after the execution. So this has already gone somewhere else after the execution. We need to change that value. So we again add a little bit more size to the input. Let it be 412 this time. We keep moving instruction by instruction until we reach the call command. So this time there are 12 Bs in the RBP, in the memory address pointed to by RBP. So we go to the next command, that is the leave command, after which RBP will get the value of 8 Bs. So something else has also happened here, that is the value of RSP has 4 Bs in it right now. So from the 12 Bs, 8 Bs has gone to RBP and the rest 4 have gone to RSP. So we also know that on execution of ret command, what happens is it sets the value of RIP to the value pointed by RSP. So we will execute the next command and see what happens. So what has happened is the value that was pointed to by RSP has become the value of RIP. So from this we understand that we can change the value of RIP and in turn control which is the next instruction being executed. Now in a 64-bit system we need only six values instead of the 8 bits. Only 6 bits are being used to map the memory locations. So we add 6 to the previous 408, giving 14. Now if we run the command or the program completely, we see that we have got a sig error even before exiting the program. So this is the error that we are trying to create, and not the error, this is the value that we are trying to overwrite, the value of RIP. The value of RIP has now completely been overwritten with Bs. So if we provide the value of the return address at this point, that is the last 6 values when giving in 412 input, we can change the value of RIP to the one that we want. Okay, so now what we need is we need the value of the return address or the place to which we need our instruction to continue to. To find that, in a similar fashion we can simply run the command and go until the call statement. So now we know that whatever part of the memory is relevant to us has been filled with Bs. Now we will try to see a map of the memory. So we will see parts of the memory that is close to our stack pointer. Okay, so we know that the stack pointer has been filled with Bs, or the area near stack pointer has been completely filled with Bs, that is our buffer has been filled completely with Bs. Now what we need is a value which is close to the middle, somewhere close to the middle, just to be safe, so that it falls return once the function returns, it falls somewhere in the no op section which we will create, and go on until it finds the shellcode which also we will be adding. So for that, let's select maybe DD30, which is somewhat in the middle. Okay, now we are actually going to compile an input which will help us launch the attack. So we have a total of 400 spaces, in which maybe we will fill in 300 with no ops. Okay, so the no op part has been done. Now what we need is the shellcode. So I have already found a shellcode that launches a new shell. and this is of size 27. Okay, so right now what we have is 300 of no ops, so this part will be 300, and the shellcode of 27, so that is 327, and then we maybe let's put some junk, let it be b itself. Okay, we have to find how many b's we need, but before that we need the memory address. So we had decided on putting the memory address as dd30. So for putting in the memory address, we need to account for the little endianness of storing the memory address. Okay, so accounting for that, dd30 will become 30dd. Okay, now we know that the final return address is of length 6. So we have 6 here, 27 here, and 300 here. So the total that we are aiming for is 414. So the value here will be 81. $327 plus 81 plus 6, which will give 414. Okay, now we will run the program again step by step. So we will use the ni for the next instruction and go until the call. So after this call, what will happen is RBP has become 1, 2, 3, 4, 5, 6, 7, 8 B's, and whatever the value we have added or the return address that we have given. So as you can see, now we have fallen into the no op sled. Now we keep going, or instead of this we can simply put C to continue execution, and we see that we have got a new terminal running, or we have started a new shell. So what has happened is we have reset the value of RIP, and we have gone back to the point that we had put into the return address, and we have fallen in the no op sled, and we reached the shell code going through all these no ops, and the shell code got executed. So that's it. We have got a new shell running inside the GDB. Now let's try doing it outside the GDB. Okay, so for this, let's hope that it works, and what we need to give it, the input what we need to give is the same as what we had given inside the GDB. So we will simply copy it. Okay, so this is the input that we gave. We will copy that. Okay, there it is. So as expected, we have gotten a new shell, and that's all. So that is how a buffer overflow attack can be implemented in an Ubuntu system. Thank you.